Hello everyone, I'm Qianwen Xu, Assistant Professor in Electric Power and Energy System at KTH. It's a great pleasure to share our project, Autonomous Coordination and Control of Smart Converters for Sustainable Power System. Our electric power system is changing to achieve the national target for 100% renewable energy by 2040. There are increasing integration of renewables into electric power systems. However, the intermittent renewables increase the risks of grid instability with the voltage fluctuation, frequency deviation, and inertial issues, which limit the further integration of renewables. On the other hand, the renewable interface converters offer new opportunities to provide various functions for grid support. To efficiently utilize the grid support capabilities of converters require optimized coordination of a large number of converters. However, optimal coordination is a significant challenge. First, the converters have different functionalities for grid support, like voltage support, frequency support, inertial support. Then how to decide when to operate at which function for so many converters to optimize the grid performance is challenging. Moreover, a large-scale grid have hundreds of converters, then computational and communication burden. If coordination of so many converters are large, then how to develop a communication efficient solution is an urgent challenge to be addressed. So this project aims to develop smart autonomous power converters for optimal support of electric power system and build a new control framework based on digitalization and AI to provide optimal grid support functions and enable further integration of renewable energy sources. This is achieved by a novel combined optimization and control algorithm for coordination and AI-assisted scheme for autonomous control of smart converters. So the first part is about novel combined optimization and control algorithm for coordination of smart multifunctional support. Here we assume converters can operate in different modes to provide different grid support functions: voltage regulation, line overload mitigation, maintenance management, and resilience enhancement. We propose a two-level framework. The upper level is optimized by a central controller, which takes the system-wide information and the forecast. And the operating mode of each converter is determined hourly by solving the proposed mode adaptive optimization model. Here, 1 hour forecasts and the corresponding Here, 1 hour forecasts and the corresponding simulation help construct the confidence set for estimating the probability of uncertainties. Then, at the lower level, set points are determined every 15 minutes based on the solved modes. A two-stage robust stochastic model is formulated that first stage is to select mode and the second stage is to decide the set points. The flow chart of the whole process is like this. At step 1, based on the hourly forecast and simulation, we establish a two-stage model and solve the optimal mode of each converter. And at step 2, we solve the second stage model to give optimal set points of converters. The proposed framework maximizes the flexibility of converters to provide different grid support functions and enhance the overall resilience. Case study is conducted for a 33-bus system with 4 converters, and the converters are scheduled to provide different support functions. Here, the mode adaptation and corresponding set points are presented. And here we show that converters can change mode to provide maintenance management, and the load loss can be reduced significantly compared with conventional methods. Here, we can see that converters can change mode to provide voltage support and significantly reduce load loss compared with conventional methods. Similarly, the proposed method can provide a line overload mitigation function to eliminate line overload. Also, mode adaptive will significantly reduce load loss compared with the conventional method. However, The previous work is based on centralized optimization. It requires huge communication and computation resources. Therefore, distributed methods are required to reduce communication and computation burden. However, for model-based distributed algorithms, we still have hundreds of iterations to converge to global optimal. That high communication is required. Recently, machine learning methods are popular for distributed operation of power systems like deep reinforcement learning. However, most of applications were pure data-driven, which result in infeasible results with security violations. So here we propose an AI-based scheme to accelerate the conventional distributed algorithm while still guarantee the optimal solution with safe constraints. Here, our idea is based on the observation that in the convergence process of the distributed algorithm, there is a clear trend. Yeah, and it can be regarded as a time series regression process, which can be estimated by machine learning-based methods. As ADMM is a popular distributed algorithm, and LSTM is an effective machine learning tool to predict time series data. So our solution is designed as LSTM-assisted ADMM algorithm. It consists of two phases. The model training phase. In the model training phase, the historical data, including the load and the distributed energy resources data, is brought into the optimization model. And the optimal operation strategy is solved with the conventional distributed algorithm for each historical child. Then the changes in dual and global variables are recorded to train the LSTM model. Then in the application phase, we have first few iterations and then use the trained LSTM model to regress their converged values to accelerate the convergence. This is the algorithm. We first use the ADMM, which is a classical distributed algorithm, to get first a few iterations of dual and global variable and feed them to LSTM model to predict converged values, and then continue with ADMM to get the final converged solution. Here, LSTM is used to predict parameters of the distributed algorithm to speed up the convergence process. Therefore, distributed algorithm is still determined by solving the optimization model. Therefore, we can guarantee the constraints and the optimality of the proposed method. A case study is conducted for this IEEE 33 bus system. And we compare the proposed method with the conventional method. We can see in the normal condition, the proposed method can accelerate 2.88 times compared with the conventional distributed algorithm. And in the line overload condition, the speed up ratio is 2.87. And in the voltage regulation condition, speed up ratio is 2.4. Maintenance condition, the speed up ratio is 9.8. Also, we show the operation points obtained by the conventional ADMM, the proposed algorithm, and the centralized optimization method. We can see that the operation points obtained by different methods are the same, which shows that the optimality and the safety are all guaranteed by the proposed method. So for our method, we provide a scientific foundation of great support based on smart converters needed to construct tomorrow's smart power generation system, add significant value to the digitalized electric power industry, and enhance the resilience of electric power system with large-scale integration of renewable energy. These are the corresponding references. Thank you very much for your attention.